All right, today is the payoff of the work that we did in the previous section. In the previous section, we learned about the unit circle and used it to develop extensions, create extensions of the definitions of sine and cosine and tangent. That, of course, could be negative in certain cases. And like the question, of course, is like, why would we do this, right? Like what's the payoff? What's the point of all this? What does this do for us that we couldn't have done previously? Well, today is the answer. Okay, so we would like, of course, right? Here's the goal of this class: to be able to solve for unknown sides and angles and triangles where it should be possible to find those values, where it would seem like they exist. Now, if the triangle is right, of course, we can solve for unknown side lengths and angle measures. We could perhaps, like if we know two side lengths, we can use the Pythagorean theorem to get the third side length. Or in other situations, like if we know one acute angle on one side, we could just do straight trig. And we could do trig with the ancients there. That is, just use trig functions that are defined for acute angles. So in that context, the context of a right triangle, we don't need updated definitions of the trigonometric functions, but we would like to be able to find, for instance, I don't know, let's say that you had a triangle of side lengths, I don't know, 4 and 7, and it included angle measure of 23 degrees. Well, that's the side angle side pattern. And what that really means is that everything is set about that triangle. The final side length has to have a particular value. The final two angle measures have to have particular values. Okay, they cannot be any different than what they are. That's just another way to put side angle side congruent. So one would hope to be able to solve for these, right? And the payoff of our extended definitions of the trigonometric functions, so that they now allow us to take sine, cosine, and tangent of non-acute angles, is that we can handle cases like this. Okay. Now, initially, it will perhaps seem far from obvious how it is that that could be done, because the trigonometric functions are built for right triangles, and as we saw in a discussion of the unit circle, even on that extended definitions, right triangles are involved, in a different way than they were previously, but right triangles are still involved. So the question becomes like, how can we do trig, or how can we use trig to solve for unknown side lengths and angle measures on non-right triangles where it should be possible for us to do so. And that's what the topic is for today in section 8.8. And there'll actually be two results, typically called the law of sines and the law of cosines. Called laws because they have an algebraic form, but they're just theorems. We will be able to use the law of cosines and the law of sines to solve for unknown side lengths and angle measures in non-right triangles. So let's talk about how we'll do this. Okay, so the initial hurdle is this. Okay, so the definitions of the trigonometric functions, whether the old ancient Greek definitions or the modern updated definitions that make use of the idea of a directed line segment, all ultimately involve side lengths in right triangles. Okay, now those right triangles can potentially have directed line segments for legs, which means that their lengths can be negative. On the modern view, that is possible, but still, ultimately, they all concern or all involve right triangles. But I just said we wish to use trigonometry now for non-right triangles, so that would seem potentially inconsistent. How could we do this? Well, the way that we clear this hurdle is that we drop in altitudes. Okay, and what is an altitude? An altitude in a triangle is a segment from a vertex to the line through the opposite side perpendicular to that line. That is, it's just a perpendicular from a point to a line, which we know from the previous chapter always exists. So an altitude can always be constructed from any vertex of a triangle. And when we do this, we get right triangles. And then we can do trig, okay, and potentially solve for those unknowns whose values we should be able to find. And then the payoff of the work that we did in the previous section is that, of course, sometimes these angles will be non-acute angles, right? And we now know how to make sense of the trigonometric function applied to a non-acute angle, okay? So we should be able to do it. So here's an example of the sort of thing that I have in mind about how it is that we can clear that hurdle that we don't have a right triangle, and how do we do trig if we don't. So here's a triangle RST, and I didn't give its angle measures, but let's just assume that it's acute, okay? That is, each of the angles R and S and T are acute angles, as they for what it's worth, appear to be, but let's assume that they are. So if we were to say something like, I don't know, the sine of r is, and I've had students do this before, the sine of r is equal to st over rs, perhaps hop back to the diagram again. The sine of r is, sorry, what did I say? St over rs, here we go. St over rs, because, I don't know, angle t looks a bit like a right angle, though it's actually not. If this is an acute triangle, that equation once again of sine of r is equal to st over rs, that's just false, okay? Because sine is also always a ratio of side lengths in a right triangle. Now, in the modern definition, those side lengths can be directed lengths, so they can potentially be negative. But it's always a ratio of side lengths in a right triangle, okay? So that's just false. So don't do that. Don't treat a non-right triangle as if it is a right triangle. Don't use the trig functions in a triangle that is not right. And so the question then, of course, becomes, well, what do we do to make the trig functions applicable in this case? Well, the answer is this. We drop it in altitude. So just to show an example, I dropped in the altitude from vertex t to the line through r and s. You see it there that terminates at the point z. And then now we can apply trig functions. We can absolutely say that sine of r is tz, the opposite leg over rt, the hypotenuse. Okay, and notice that we made this point in the discussion of the updates to the trig functions in section 8.7 that though this is the form of the ancient definition, the ancient definitions are perfectly consistent with the modern definitions. Okay, so whether ancient or modern, this is perfectly correct. And now note that this would also work if our angle was not an acute angle, okay, because our modern definitions of the trig functions work for angles that are not acute. All right, so here's something that you'll prove, the first of the two laws for the day. I won't go through the proof here with you in the PowerPoint. Instead, I'll leave the proof to the problem set where I guide you through it. It's a table proof, mostly algebra with just a little bit of trig involved. But the result of this will be the so-called law of sines. So what it says is this. For any triangle, RST, whatever it's called, in this case triangle RST, with angles capital R, capital S, capital T, side lengths little r, little s, little t, with, as always, the lowercase letter opposite its uppercase counterpart, so little r opposite big R, and so on. This equation that you see, this extended proportion, must be true. Little r over the sine of big R equals little s over the sine of big S equals little t over the sine of big T. Okay, these ratios must all be equal. Okay, so another way to put it is this: is that in a triangle, any triangle at all, the ratio of a side to the sine of its opposite angle is a constant. Okay. It is the same value no matter which side and its opposite angle you have picked. Okay, so that is the law of sines, and we're about to see how it's used. And a nice way to put this, the way that I often put it, and I would like you to understand what this means when I say it. The law of sines really says that in a triangle, sides are proportional to the sines of their opposite angles. Okay, that sides are proportional to the sines of their opposite angles. And that just means, to go back to the formula again, that if I take a side and form with that side the ratio to the sine of the opposite angle, and do it again for another side and again for a third side, as you see in the formula, that those must all be equal values. So sides are proportional to the sines of their opposite angles. And this is perhaps the nicest and easiest way to put it, the law of sines. And it is also a correction to a mistake that students sometimes make. I've had, I think every year at some point along the way, at least one student will ask me or just assume that in a triangle, sides are proportional to their opposite angles, not to the sines of their opposite angles, but just to the opposite angles themselves. And this is false. Okay, it's easy to build counterexamples to this. So we know, for instance, that in a 30, 60, 90 right triangle, the hypotenuse is double the length of the side opposite the 30-degree angle. So the ratio of the sides here, 2 to 1, is not the same as the ratio of the angles, which is 90 to 3, which is 3. Okay, so sides are not proportional to the opposite angles. They are proportional to the sines of their opposite angles. All right, so Let's solve for t in the diagram below. And the reason why, as will emerge as we solve through this problem, why the law of sines is applicable, is the nature of the information that we have. Okay, so we have two angle measures in the included side length. That is, we have the angle side angle type pattern. And if we have the angle side angle type pattern or the angle angle side type pattern, the law of sines will work beautifully to solve for an unknown side length. And in this case, we wish to solve for little t, the side length opposite angle t. Okay? And as just a note about this, we know that, as it were, angle side angle and angle side are like convertible one to another because we have the triangle angle sum theorem. So if we know two angles in a triangle, we can find the third angle. So any instance of angle side angle is also an instance of angle angle side. So what do? Well, we apply the law of sines, which says, as I have noted, that side lengths are proportional to the sines of their opposite angles. So here's what must be true. T over the sine of its opposite angle over the sine of 79.54 is equal to, well, let's see, the same for any other side opposite angle pair. Well, the only side we know is 1.12, right? So we're going to have to use that. And then we need to place it over the sine of its opposite angle. Let me clean that up. Over the sine of its opposite angle. Well, in this case, of course, we'll actually need to find the measure of that angle. So this will be the sine of angle S. And what is the sine of angle S? Well, we need to do just a little bit of algebra to find that out. Well, not algebra, just simple arithmetic to find that out. And I think I'll stop right there. So don't want this to go on forever. Just simply find the measure of S by the triangle angle sum theorem, plug that in, and then solve out this proportion. Okay, so just cross multiply and solve it out. That's a simple matter. So that's an example of how it is the law of sines would apply in this case. And notice that this works also for obtuse angles as well, okay? Because we have updated our definitions of the trigonometric functions, and it now makes sense for us to take sine or cosine or tangent of non-acute angles, so obtuse angles. So even if our triangle is obtuse, the law of sines will work beautifully, okay? So let's see, what do we have in this case? In this case, we have the angle-angle side pattern, right? We have two angles on a non-included side. And of course, we could find the third angle as well by the triangle angle sum theorem. So this also could be thought of as an instance of angle side angle. And again, angle side angle and angle angle side, those are the cases where the law of sines works for us. So let's write down the equation that would allow us to find the value of s, little s. So what does the law of sines say? It says write down its side length. Place that over the sine of the opposite angle, the sine of 108.81, and that is equal to, well, let's do it again. So in this case, we wish to find s, so we'll place that into our proportion. And then that will be placed over the sine of s. And again, I'm not going to take the time to solve this out completely to do all the details. You would find the measure of s by means of the triangle angle sum theorem. And then you've got a proportion. You can just cross multiply and solve it out. And let me emphasize this, okay? Previously, before we updated our definitions of the trigonometric function, the sine of 108.81 degrees would have made no sense at all. But now it makes perfect sense. And it is what every calculator says that it is. All right, so just to reiterate what it is that you use the law of sines when it will work, and we've seen that it works in these cases. If you have an angle-angle side or angle-side-angle type case, that is if you know two angle measures and a side measure, however they happen to be situated, then law of sines will work beautifully. You might need to make use of the triangle angle sum theorem to find the third angle before you make use of the law of sines, but of course that's a simple matter. All right, so now, law of cosines, which I know will initially look more complex, and I suppose that it is. And once again, I will not take the time to prove this with you here in the PowerPoint. Instead, I leave that for the worksheet there. I guide you through the proof. It's a table-style proof, and you can simply fill it in. It's a little bit of trig and mostly algebra, honestly. And then we get this result, okay? And notice that it appears to be three equations, and it is, okay? But as we'll see, each of these equations has the same form. So let's pick these apart. Let's parse these to understand what's really been said. So the first form says that remember that lowercase letters are side lengths, uppercase letters are angle measures, and the lowercase is always opposite its uppercase counterpart. The first version of this equation says that r squared is s squared plus t squared minus 2 times s times t times the cosine of r. Okay, so what it's really said is this, if we just speak generally. It says that a side squared is the sum of the squares of the other two sides minus twice the product of those other two sides times the cosine of the angle in between them. Okay, of course, capital R is the angle in between little s and little t. So again, what this says is that a side squared is the sum of the squares of the other two sides minus twice the product of those other two sides times the cosine of the included angle. And the other two forms of the law of cosines have that same general form. Okay, so the second, which says that s squared equals r squared plus t squared minus 2rt times the cosine of s, that says that a side squared equals the sum of the squares of the other two sides minus twice the product of those two sides times the cosine of their included angle. And then the final form says that precisely as well. Now, just to note this isn't essential to the work that you'll do, but it is, however, like conspicuous. You might notice that this looks like an altered form of the Pythagorean theorem, right? So if you were just to look at the first part of each of these, like r squared equals s squared plus t squared, that looks like the Pythagorean theorem, of course, right? And it would be exactly true if r were the hypotenuse of a right triangle and s and t were its legs, right? But we have this other factor, this minus 2st times the cosine of r. That's like, the way I like to think about it, it's like a correction factor, okay? It corrects for the fact that we do not have a right triangle. So instead of, I don't know, maybe just approximately equal if the angle was approximately right, or just like plainly false if it's not close to a right angle, the correction factor corrects for the fact that this is not a right triangle. Okay, so this is like an extended or a generalized form of the Pythagorean theorem. We'll find actually that there are multiple ways in which the Pythagorean theorem can be generalized or extended, but this is one way. Okay, this is absolutely one way. Oh, and I have a little question for you. This is a question that I will ask on the problem set, and if you don't understand right now, you'll have an opportunity there to think about it. But there is no reason to exclude the use of the law of cosines or the law of sines in the case of a right triangle. Okay, they're not necessary. They're more power than you need if you have a right triangle, but they're perfectly true in the case of a right triangle as well. So what if it were the case that angle R were a right angle? Okay, so in that case, we would have r squared equals s squared plus t squared minus 2st times the cosine of r. That would be times the cosine of 90 degrees. Oh, but in the case of a right triangle, r squared is just simply equal to s squared plus t squared. That's just it, right? There's like no correction factor. And you can ask yourself then what the cosine of r would have to be in the case that r is 90 degrees. What would have to happen to that term, 2st cosine r, in the case in which r is 90 degrees? Well, of course, the conclusion is this. Sorry about that. The conclusion is this, is that that factor would have to be simply 0, right? There is no correction to be made. And how is it that that correction factor becomes 0? Well, the cosine of 90 degrees is 0. You'll have an opportunity to think more about this on the problem set. All right, so here's an example of what it is that we can use the law of cosines to find an unknown side length. Okay? Notice that this is the side angle side type case. So what we saw previously is this, is that if we had the angle angle side or angle side angle type case, use the law of sines to find an unknown side length. If we have the sine angle side type case, we can use the law of cosines to find that third side. Okay, so how does this go? Well, remember that general form of the law of cosines. It says this. It says that a side squared, and this is really the way that you should remember it. A side squared is equal to the sum of the squares of the other two sides, so 1.19 squared plus 1.11 squared, minus twice the product of those two. So minus twice the product of those other two times, and this will have to go on the next line, times the cosine of the included angle, so 103.57 degrees. Okay, so that's what the law of cosines tells you. And then I won't take the time to actually churn through this with a calculator, but it is just a simple matter. Okay. And do note that your calculator does make use of the modern updated definitions of the trigonometric functions. So your calculator will be quite delighted to take the cosine of 103.57 degrees. It won't complain at all about that, right? So just simply plug through this, plug the right side into a calculator, and then of course take the square root of both sides, and that'll give you the value of t. All right, now let's talk about how it is that we could use this to find the measure of an angle, okay? How we could use this to find the measure of an angle. Well, it's not entirely clear how our formula would work in that case, okay? Let's see how the details are going to work out. So let's say that we're going to find the measure of angle S. Well, that means that we wish to use the version of the law of cosines which will involve the angle S. And which version of those three equations that we saw will we use? It's the one that starts with little s, right? So here's what it will be. It'll be 0.94 squared is equal to 1.36 squared plus 1.87 squared minus twice the product of those two, 1.36, times 1.87, and once again, I'm going to have to go down to the next line, times the cosine of s, okay? Times the cosine of s. So let's think about that, okay? Let's think about that. How are we going to solve for s in that case? Well, we're going to have to first of all isolate cosine s. So let's do this in stages, okay? So let's first of all subtract 1.36 squared from both sides and 1.87 squared from both sides. And then what will we have? Okay, so on the left-hand side, we'll have 0.94 squared minus 1.36 squared minus 1.87 squared is equal to negative 2 times 1.36 times 1.87 times the cosine, sorry, let me clean that up, times the cosine of s. All right, so again, go solve for cosine s, and then we'll think about how we'll actually get s out of that. Well, what are we going to have to do at this point? Well, we've got factors. We've got quantities multiplied by the cosine of s, so we'll have to divide by all of those. So we'll divide both sides by negative 2, by 1.36 and 1.87, and here's what we'll get. And I'll go ahead and turn this around and place cosine s first. So it's going to be 0.94 squared minus 1.36 squared minus 1.87 squared all over negative 2 times 1.36 times 1.87. Okay, so, just basic algebra. So let's think for a moment, okay? That's what the cosine of s is. Okay, so the cosine of s is that ratio, and you can plug it into a calculator and get the value. And then ask yourself what s itself would be, okay? What s itself would be? Well, hopefully you recall our work with the inverse trigonometric functions. If the cosine of s is that ratio, then s itself is the inverse cosine, which I'm going to write as cosine with the superscripted negative 1. As we learned, you could also call this arc cosine, ARCCOS, of that entire quantity. So 0.94 squared minus 1.36 squared minus 1.87 squared all over negative 2 times 1.36 times 1.87. So s will be the inverse cosine of that, okay? Will be the inverse cosine of that. And at this point, again, I won't take the time to actually plug this into a calculator. One can go and plug this into a calculator. That is, do the computation there contained in parentheses and take the inverse cosine. A small note here, if you don't do the calculation right, it's entirely possible that your calculator will complain when you attempt to take the inverse cosine. That value that's contained within parentheses will have to ultimately be between 1 and negative 1. If it's not, you've made a mistake. But if it is, you can take the inverse cosine and you can get an angle value. And then, as I tell you on the homework assignment, There are many online calculators, triangle calculators, that you could use to check your work. As a matter of fact, in the homework assignment, I linked to one that I have created myself, and you can check your work. But that's how the algebra goes. Okay, that's how you solve for the value of s. And then just final note here. When is it that we use the law of cosines? Well, we use the law of cosines when we have the side angle side or the side 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 type case. And the side angle side type case, we'll use it to find an unknown side length. And in the side 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 type case, we'll use it to find an unknown angle.